Okay guys, so the purpose of this video is essentially to kill kind of two birds with one differential stone, so to speak. Okay, so the first reason is for us to be able to find the gradient of the exponential function, and by doing this, we're going to use implicit differentiation to do this. By doing this, we're going to find out how this relates to e and what this number e really is. Okay, so to do this, first we're going to look at these two graphs here. So this one in the pink is y equals 2 to the x. The one in the black is actually the curve of its gradient function. Okay, and similarly this pink one here is y equals 3 to the x. Okay, and the black one is its gradient function. So what we can see straight away is that the gradient function of both of these curves are very similar to the original. You can see that y equals 2x is here. The gradient function is less steep, but exactly the same shape. And similarly, y equals 3 to the x and its gradient function are extremely close, but the gradient function is more steep, or steeper than the y equals 3 to the x. What e is then, and how this relates to e, is that for y equals e to the x, the gradient function and the original function y equals e to the x are the same. They match each other, they're on top of each other. Okay? So let's prove this algebraically. Let's prove how I even got to this point anyway, saying that the gradient function is just essentially a multiple of the original. So what I do is I start with y equals 2 to the x. I'm going to log both sides, which will give me, from our rules of logs, log y equals x log 2. And by the way, this log here, this ln, this is the same as log base e, okay? Log base e. And it's denoted on your calculator and for us as ln. And we're going to be using this a lot, okay? In C3 and C4. So, we're at this stage here. And they're going to differentiate both sides. So implicit differentiation from the other video, I get 1 over y times dy over dx equals log 2. And then of course I have dy over dx equals y times log 2. And we know from here already that y equals 2 to the x. So I get 2 to the x times log 2. And log 2 is approximately, if you type it in your calculator, is approximately 0.6931 ... So actually you can see that the gradient function of y equals 2 to the x is 2 to the x times this number here, which is obviously less than 1, which explains why this black curve is less steep than its original. Let's do the same for y equals 3 to the x. So log both sides gives me log y equals x log 3. Okay, and then differentiate both sides. So d over dx log y equals d over dx x log 3. Implicit differentiation 1 over y dy over dx equals log 3. Let's bring over the y, and I get dy over dx equals y log 3, and we know we started with the y value, y equals 3 to the x. So therefore my dy over dx equals 3 to the x log 3. And log 3 is approximately, put it in your calculator, 1.0986 ... And this explains why the gradient function here of y equals 3 to the x is so close to the original, because this is very close to 1, isn't it? Okay, it's slightly larger than 1, and that explains why it's slightly steeper. And I said at the start of this video that e to the x has the same gradient, so actually the number timesing e to the x is actually going to be 1, and that explains y equals e to the x. When I differentiate it, I get dy of dx equals e to the x. Okay? And the reason that, well, the way I would find this magical base, okay, this magical base here that would give me the same gradient as the original, is I could use try and error, because the base must be between 2 and 3, mustn't it, to get this number here timesing itself by 1. So I could try maybe 2.5, which would give me a number. And then I would try 2.7, I'd get closer and closer and closer, until the point where I find this e value, which is 2.718, ... goes on forever, okay? So I would have y equals e to the x, and dy of dx equals 1 times e to the x, so the same as the original. So that's the first thing we must know, that when you differentiate e to the x, you get e to the x again. The other thing we can find from this is our general formula then for differentiating the exponential function. So if I start with y equals a to the x, I can see from the work that I've just done that I get dy of dx equals a to the x log a. So this is our general exponential differentiation formula. Okay. So let's see, if I had y equals e to the x, dy of dx equals e to the x times log e, doesn't it? Now remember, at the start of the video I told you that ln, log, is the same as log e. So actually, and what I'm saying is, I've got log e, base e, which of course is 1. And this explains why dy of dx would equal e to the x times 1, which of course is the original here. Okay? So, that's done.